properties of stuff that you've already done. But what's going to be different is that we're going to treat them in terms of fractions. For example, x cubed times x to the fourth. What did you get?
X to the second.
What did you do?
I added the x.
Yeah, when you have the same base with different exponents and you're multiplying, all you're doing is adding your exponents. Okay? I don't even want to know. After that, we also did this. If you had x squared to the fifth power, what would you do? Yeah, power to power. You multiply. What do? You play war, good. You play war, you subtract and go from there. So you'd wind up with x to the sixth. What if it was x to the eighth over x to the 12th?
You move it over so you get 1 over x.
Oh, so you keep the 1 there. It doesn't miraculously float upward?
You found that?
Oh, a lot of you did on the last question on the test.
I don't know what I got. I can't remember the test. It's just so stressful.
Okay.
My memory just got
So what happens here is we're gonna use all of these same properties, but we're gonna use with fractional exponents, which means you just gotta remember how to add fractions. So let's go through a couple of these, one at a time. We have the property where you have the same base and you're multiplying. So if I have the same base and I'm multiplying for it, you don't need to have the unit circle out yet. Same base, different exponents. You add the exponents. What's 1/2 plus 3/2? 4 halves, otherwise known as 2, which equals 9. There you go.
Wow. Give me a hard
Power to power, same idea. If you have the same base, or excuse me, if you have any base raised to an exponent, so we have 4 to the 3/2 squared. Unfortunately, the book uses slashy fractions a lot, whereas I hate slashy fractions. Try to rewrite them as regular. It's just a little bit easier to visualize, or actually to see what's going on. When you multiply fractions, you gotta remember, you're multiplying straight across. Go figure, that's what we just did. You get 4 cubed, which is 64. 64.
Oh.
Is it 64?
Yes.
No.
36. 4 times 4 times 4.
When you have stuff within parentheses all raised to the same power, remember that's kind of the same idea as distributing the power to both terms. Works the same way when you have fractional exponents as well. You can work yourselves inside out if you'd like, because order of operations tell you to take care of the interior first. So if you have 9 times 4 to the 1/2, 2 ways you can go about that. Distribute the power, you get 9 to the half times 4 to the half. What's 9 to the half power? 4 to the half power, which is, or I could have done it this way. Order of operations tells me to work inside out, and I still get this exact same thing. Okay? Very similar to what we have done in the past with just integers, but now we're going to start talking with rationals, so we're going to have fractions. Okay?
I'm okay with that.
Same deal, negative exponents, they are not happy. When exponents aren't happy, we make them happy by moving them to the denominator or moving them to the numerator if need be. So if I have 25 to the negative 1/2, well, that 25 is no longer happy. Make them happy. 1 over 25 to the half, otherwise known as 1/5.
Let's go.
Having to remember what's larger when you're dealing with fractions can be sometimes daunting, especially if it's not halvesies. If it's a third and a fourth and things like that, you'll have to try to remember how to get yourselves quick common denominators. Yes, sir.
Are we gonna get like the really big fractions like last time as exponents?
Oh, yeah. Oh, yeah. I love fractional exponents. They're great.
Yeah.
I sense sarcasm in that, yay.
That was a mistake. He's going to plus one.
So what is that? It's a 6. So it's 6 to the 5/2 divided by 6 to the 1/2. Do those guys have the same base?
Yes.
Yeah. What's bigger, 5/2 or 1/2? So what's 5/2 minus 1/2?
4.5.
Otherwise known as 2. Okay? Same idea. You're just still playing the same rules. You're still playing war. You're still working yourself through. If the 5/2 was larger than the denominator, it would just move itself down to the denominator. Same thing works.
Wait, so where did 6 come
This is, I skipped the step. This was 6 to the 4/2, which is 6 squared. 5/2 minus 1/2 is 4/2.
I can really read that on the short side.
Where's your glasses?
I haven't got them yet.
Why'd you sit up closer?
Wait, yeah.
Shut your mouth. You don't remember. I'm tired of you.
I haven't had this.
What is that block there?
Well, I haven't had the answer.
Bella, is it so blurry? Yeah, actually.
Same idea here. I have a fraction all raised to an exponent, which means that I can distribute the exponent to both numerator and denominator. So if I have 8 over 27 all to the 1/3 power, means the same thing as
Sorry.
It's all right. So you get 8 to the 3rd, 27 to the 3rd. What's the cube root of 8? 2. Cube root of 27. I get 2/3. Okay. Which means we can combine properties and things and stuff and make a mess of everything. Which makes life fun. Bless you. Let's start with this. 5 to the 1/2 times 5 to the 1/4. Do they have the same base?
Yes.
Yes.
Base is this. Do they have the same base? Base, exponent. Base, exponent.
Yeah, they have the same.
So they have the same base. And they're
You missed a
multiplying, so what do you do to the exponents? What is 1/2 plus 1/4?
3/4.
A lot of people have asked this, when do you rewrite things with nth roots versus exponents? If you start with an exponent, generally you keep it in an exponent. When you start in nth root, you usually leave it as nth root. There will be times that it is easier to simplify using fractions as opposed to using nth roots. And I'll show you that as it comes up, okay? And you'll start to pick and choose. Some people think it's easier with nth root. It's totally up to you. I'm not going to tell you one way or the other, but there are tricks to some of these things. So. So in this first one, I have 8 to the 1/2 times 5 to the 1/3. Can I combine those two? I cannot because they have different bases. So in this case, I have to start the problem by distributing out the power. So this becomes the power to power problem. So what is 8 to the 1/2 squared? 8, very good. This becomes 8 times what? When you do power to power here, what's 1/2 times 2? 1.
Oh, got it,
Oh,
okay.
5 to the 2/3.
Very good.
Um,
And that would be my answer. It'd be 8 times 5 to the 2/3. Yes, sir. Okay. And the reason I'm doing that is because I can't figure something out. Yes, sir.
Could you not change the fraction proportionally like in the movie?
What do you mean?
Like, could you not multiply both of the things by, make it 6?
No, because you have different bases.
So you can't change it, like you can't, since,
If they were both 8, if it was 8 to the 1/2, 8 to the 3rd, then yes, you can do that. But since it's the 8 and 5 with different bases, you cannot. You can only combine them if their bases are the same. Same deal on the bottom one here. In this case here, everybody notice they both have the same exponent, but they have different bases. But look what happens here. They're being raised to a negative exponent. So they're both going to go to the bottom because, well, what's 4 times negative 1/4? Negative 1. So I'm going to get 2 to the negative 1 times 3 to the negative 1, which is 1 over 4. 6. Becomes 2 times 3 then. All right? Sorry, let me slide this up for you. Should probably be able to look at that one and tell me the answer without doing any work.
1 over 1/3.
Okay, let's try this again. Let's do the work. 7 divided by 7 to the 3rd. Hey, what's going on? You want to come in and do more math? You got to run through a card trick today.
let's do it again for math.
Anyway, if I'm looking at 7, good, how are you? If I'm looking at the 7 divided by 7 to the 3rd, who wins in the Battle of War? 7. What is the 7 in the numerator's exponent?
1.
Otherwise written as? 3/5. Very good. So what's your final answer?
7 and 2/3.
Very good. Does that make sense now?
No.
Yeah, it makes perfect sense.
oh, yeah, but
Who wins the Battle of War?
I got it, yeah, okay. I was thinking of
I'm a good writer. Right professional.
All right, let's try this one.
Believe whatever you want them to.
In this case here, I have 12 to the 3rd divided by 4 to the 3rd. That means basically I'm looking at the cube root of 12 divided by the cube root of 4. We okay on that?
Yeah.
So here's, there's no equal sign. Here's what happens. What I'm going to do here is I'm going to rewrite these two exponents as unpower to power. Watch what happens. Isn't that the same thing?
Yes.
I undistributed the power of 1/3 to the fraction. Since they both have the exact same exponent, I'm going to take that exponent out. Because now, what's 12 over 4? 3. By doing this, since these guys have the same exponent, I can simplify because what I'm looking at is, move this up here, oops, is the cube root of 12 over 4, is it squared?
Yeah.
Squared. It's the same principle. You guys were able to simplify square roots kind of the same way. Because square root of 6 divided by the square root of 3 equals square root of 2. It's the same thing with nth roots. No, what's 12 divided by 4? 3. So I get 3 to the third squared, which is 3 to the 2/3. And the reason why I'm going back to my fractional exponent is because I started as a fraction.
I was just gonna ask for.
More often than not, it'll ask you to do it that way, unless it says starts as a fraction, then write it as an nth root. But usually it's you continue. Okay? So far, so good?
Yeah.
Okay. Let's try something a little bit different. Let's think about properties. You've done this with square roots. You haven't done this with nth roots. For example, how did you guys simplify the square root of 8? 2 root 2. It was equal to 2 root 2, but what you were able to do is that you split this up into 2 different square roots. Square root of 4. And again, you simplified it and got your 2 root 2. Well, this is the property that allows you to do that, which means you can do that with any nth root, which means you're going to start to look for perfect cubes, fourths, fifths. Well, sixth, the only thing you probably ever find is like 2 to the 6th. 64. Obviously.
We go. Bad, yeah.
That's good. For example, cube root of 54. I'm going to think of a perfect cube. Very good. You got it, you got it. So what happens here is you're going to do the same basic principle. You're going to start to look for the perfect cube that goes into it. Well, cubes, you're looking at 8, 27, 64, 125, then all of a sudden it gets really big. 216, 343, and then something else I don't know. Okay, so this becomes the cube root of 27 times the cube root of 2, which is 3 cube root 2. That's how we simplify. Okay? That's how we simplify those. This would take a little getting used to. This will take a couple of 3 days or so of actually doing it more than once. You'll be all right. Same deal with division. When you're working with division, we were able to split apart our fractions. You did this when you rationalized denominators. Like number 2 on the test from yesterday, where you had the example of plus or minus the square root of 1/3, I believe. Or was that the other class? It might have been the other class. Anyway, we hadn't talked about how to rationalize your denominator in this class yet. But you did this a whole boatload last year. If you didn't rationalize, I didn't yell at you. If you forgot the plus minus, it's a bad mamma jamma. This is the square root of 1 divided by the square root of 3. Are you okay with that?
Yeah.
What's the square root of 1? 1. What did you have to multiply top and bottom by to get rid of it? Root 3. Now, would you believe it if I told you that this is the same as 3 to the 1/2, 1 over 3 to the 1/2?
I'd see you, Josh.
And if I'm multiplying it by something, I'm trying to create it to a whole number by eliminating the fractional exponent.
Wait, how the heck do you eliminate the fraction exponents if you have 1/2 times 1/2? Wouldn't that make it a 1/4?
You add them
X to the
together.
third times x to the fifth equals x to the eighth. You add your exponents.
Oh, right, I'm dumb, sorry.
You're not dumb, you just grab it. That's okay. That's okay. And this is usually what happens when I show you guys what's happening in terms of fractions, because you're not used to thinking that. We don't show you guys the rationale behind it when you're working with the fractions because you're trying to create that fractional exponent to a whole. So the whole time you guys were multiplying by 1/2 powers to make 1/2 plus 1/2 equal 1. That's how this stuff works. So you got root 3 over 3. Yes, sir?
So basically, like, is all of chapter 7 basically just applying all of the stuff that we learned in algebra 1 as far as like the way things multiply together to like
It starts.
fractional exponents?
A lot of it is, yes. And then we'll graph them. We'll graph fractional function, rational functions, and all that kind of stuff too. But we start with the basics to build off of. So let me show you an example of what you would do if you have to take a and rationalize an nth root. Okay, we're going to rationalize an nth root. 2 over the cube root of 3. When I'm rationalizing nth roots, the book doesn't usually do it this way, but I like to switch to a fraction. Because if I have a fraction, I can see what I have to add up to equal the whole. Okay? 3 to the cube root of 3 is 3 to what power? 1/3. Good. So this is the exact same thing as saying, oops, 2 over 3 to the 3rd. I need to figure out what I'm going to multiply it by with the same base to equal 3 to 1. Good. What do I add 1/3 to make it 1? 2/3. And I multiply the top and bottom by the same thing. Because what is this value equal to? 1. Whenever you're rationalizing, whether it was with imaginary numbers, conjugates, multiplicative inverses, any of those things, you're always multiplying by some factor of 1 just to change shape. Kind of like undistributing a -1 to change 1 minus x to x plus 1.
That's how you do it.
Like on the question yesterday.
I knew you talked about it, but I forgot how to do
They
it.
were
I didn't know what to do.
So now, 3 to the 1/3 times 3 to the 2/3 is 3 to the, which means there's no more radical in the denominator. But in my numerator, I get 2, 3 root 3 squared. Because I started with nth root, and I finished in nth root. Okay? It looks weird, but you've been doing it that way all along. Yeah.
If you wrote the answer as 2 times 3 to the power of 2/3, is that, first of all, is that right? And would you mark it off on the
Again, like I was saying, if you're starting in nth root, I'd like you to finish in nth root. Okay? I like to use the fractional part in the middle because I think it's easier to see what in the world is going on. All right? That's all I'm using that for. Yes? Let's try this one then, and then I'm going to give you back your stuff. I get the 5th root of 3/4.
Why do you make things so easy for us? It's
So if I go 5th root of 3/4, I'm going to start the problem by splitting it up into numerator and denominator. Right? So I go to split it up into nth roots, or could I go right to fraction? You guys be okay?
go right to fraction.
Go right to fraction, just so you can see it. So it's 3 to the 5th over 4 to the 5th. What are you going to multiply top and bottom by? Everybody okay with that? 4 to the 4/5? You see how it's easy to put it to a fraction to make a whole by doing it this way? As opposed to trying to figure out, what the heck? I always think the fractions are easier for doing this than anything else. Okay? Top and bottom by 4 to the 5th. I'm sorry, 4/5, excuse me. I'm I'm good in the denominator now. The top, go back to your nth roots. I get the 5th root of 3 times the 5th root of 4 to the 4. Okay. So it looks a little messy. What's that? Here, we'll make it pretty. With flowers around it. And some snowflakes.
What was the exponent again?
Some snowflakes. And a smiley face.
That's 2 smiley faces. Now it's 3. 4. Okay. Same.
103 fifths.
I forget what number it was.
I counted them.
It's on page.
Page 450 to 3
I think it was. I forgot to write it down.
Not when, Mr. Powers, but where? Oh, yes. Not where, Mr. Powers, but when. I know.
Get it right. How about no?
Do you guys have any? I don't know. Do those, please.
Yes, sir. Mr. Murphy, why would you give homework on the day that Star Wars comes out?
Comes out at 9. I'm totally going.
You'll get over it.
It already came out, bro.
Technically, it comes
It doesn't come out till 7.
Technically it does, but I mean, there's some other showings. What?
The first showing is at 7.
This is a little older.
Yeah.
You weren't here when I was come back a while ago. That's why.